In this lesson, we're going to be considering composition of functions. So we've already learned how to do certain function operations like addition, subtraction, multiplication, division. But we have a new operation that we've never seen before. So this is called composition of functions, and what we get are composite functions. So this operator is an open circle, and that is the composition. So that's an operator like addition or subtraction would be, but it's open, it's not multiplication, so try not to confuse it with multiplication. But what you see is f of g of x, and so when we read it, that little open circle you can read as of. Its technical name is compose. So if I compose f with g, what it means is that the g function is going inside of the f function. So it's also written as this f of, like we normally have function notation, of g of x. And the order matters in which you see these two letters. And so if I saw g of f, so g open circle f of x, what that means is that f is now going to go inside of g. So I would start with the g function, and inside of it, we're going to put in the f function, so g of f of x. And they don't have to be f's and g's, but those are the common function names that we often use. Now, a picture of this would look like if we had that input-output function operation with an input of x, and it goes into the g function. That's the first one it's going to go into. We get an output. Now that output is g of x because it went into g, and we're going to take that output and put it inside of the f function. So that becomes f of g of x. So basically we start with an x and we're going to put it into one function, take the output and put it into the other function. So let's look at what that looks like. If we have f of x is x squared and g of x is x minus 3, we want to find two different things. So let's say f of g of 5. I'm just going to rewrite that as f of g of 5. So what we're saying is g is going inside of the f function. Let's look at what that means, just backing up a few. When we had f of x is x squared, we currently have been reviewing just evaluating things like f of 3. It means we're going to take 3 and input it into the function. So what it does is replaces the x and becomes the input. You can do that with any number you want to. So it can be f of negative 1/2 and be negative 1/2 squared, give you an output. But we can also do that with expressions. And so we'll see things like, let's take the expression f of x plus h. And what we're doing is just replacing the input with whatever we want in the function. So if x is the input, that thing is being squared, that input now is x plus h. So what we're doing here is changing it to g of x. So that input is a whole function instead. Now in our function here, we've got f of g of 5. And to do that, we first need to find out what is g of 5. So first find out what g of 5 is. Okay, so we know how to do that part. G of 5 is 5 minus 3 from this g of x function, which ends up being 2. And then that goes inside of f. So we're going to take f of 2 now and put that into the f function, which is x squared. So 2 squared is just 4. So our answer ends up being 4. Now the second part of this says g of f of 7. To start that means that we're going to do f of 7 and put that inside of the g function. So let's figure out, what is f of 7? Well, 7 squared is 49, and then we put that inside of g. So 49 minus 3 ends up being 46. Now let's look at it when we have an actual function and we're not evaluating at a specific number. So it says to find the functions f of g and g of f and their domains. All right, to find the domain of a composed function, we're going to find the inner function domain and the final function domain. And then we can look at the intersection of the two. I think it's helpful when you're doing these to actually look at this with two different colors and use the input as a different color. So I'm going to do that in red and try it out on your own. See if that helps you understand this a little bit better. But we have f of g of x, and I think this notation kind of explains a little bit more of what's going on. We're going to put g inside of f. So if f is 4x minus 2, the x is your input that you're replacing. So I'm just going to leave that open for a minute because we need to figure out what are we putting inside for that input. And we're putting in the g of x function. That g of x is 3 minus 2x squared. So I used a different color to show that this isn't something new that's been put into the function, but g of x just went straight inside of the f. And now that's something that we can evaluate and try to simplify. So I would distribute my 4, get 12 minus 8x squared, and minus 2. And we could combine those to get 10 minus 8x squared. So you might see it written that way. You also might see it written as negative 8x squared plus 10. Both are perfectly fine. This second one is in standard form because your x squared comes first. And so then we want to find the domain, all right? So the domain of the function, domain of f of g, I really think it's helpful to start at the very beginning here to see, do we have any of those restrictions? Now that g of x function did not have any restrictions because it's a quadratic, and quadratics had a domain of all real numbers. When we look at the overall function, we ask ourselves mainly two questions. Are there any square roots? And is there a fraction with like x in the denominator? So are there any rational functions? And we don't have either one. So since we don't have either one, there are no restrictions in this case, which means our domain is just all real numbers, or negative infinity to infinity. All right, let's go to B. And so g of f, we need those functions again, so let me bring those back. If we do g of f, our notation has changed, so we start with g and put f inside of it. So let's look at what the g function was. 3 minus 2x squared. So 3 minus 2, and when we get to the x, I'm just going to put a set of parentheses because that's the new input, squared. And so let's see. F is going inside of the input, which was 4x minus 2. There's your f function. Now we're going to try to evaluate this. And if we try to follow PEMDAS, the order of operations, we can't combine those because subtraction is one of the last things we do. Multiplication is something we do, but exponents come first. So we would try to do these exponents before we do this multiplication. And we do that by just writing this out as 4x minus 2 times 4x minus 2, because it's squared, so it's being multiplied by itself. And we need to multiply these two binomials. And this is something that you're going to get used to, hopefully, of multiplying this out. But you would be multiplying 4 times 4, 4 times 2, 2 times 4, and 2 times 2, and kind of follow that FOIL method that we've talked about before. You'll also see there's sometimes a shortcut when you're squaring a binomial where you can just square double square. But you'll need to get familiar with what that format looks like, where you're squaring the first term, because 4x times 4x is 16x squared. You would double the product of both of these things. So when we do that, we're doing 4x times 2, which is 8x. And because we're going to have two of these 8x's, we would double them. So that gives us minus 16x. And then negative 2 times negative 2 is a positive 4, which is where that square part comes into, because we would square the last term, which gets us a positive 4. But you can always just distribute and work yourself that way. Now we need to distribute 2 to that set of parentheses to get 32x squared plus 32x, and then minus 8. So if you notice that 2 is not just a 2, it's a negative 2 because we have this minus sign with it. So I'm subtracting a 32x squared, and if I did minus a negative, that became plus 32x, minus a positive becomes minus 8. And then we combine like terms. So I get negative 32x squared, a positive 32x, and then negative 8 and positive 3 is just negative 5. Now let's look at the domain of g of f. And if I go back to the original where we had it, that input has no restriction because it's just a linear function. And then we look at the whole thing. There's no radical, there's no rational expression. So there's really nothing that's affecting the domain of this. Therefore, our domain is all real numbers, negative infinity to infinity. All right, now g of j. G of j would mean that I'm starting with the g function and putting in the j of x function inside of it. The g function was 3 minus 2x squared, but that x is being replaced. And we're going to replace it with the j function. So the j function is square root of x minus 5. So let's put that in there. And now we can simplify. When we simplify, again, we have to follow order of operations, so we're going to do our exponents first. So if I squared a square root, those two things are inverses of each other. So that's kind of going to cancel out. So we get 3 minus 2 times just x minus 5. And now I distribute, get 3 minus 2x plus 10 from distributing our negative 2. And then combine to get negative 2x plus 13. And this is why it's important to look back at the original, because if you only look at the end, that looks like there's no restriction because it's a linear function, but there is a restriction to our domain. So let's pay attention to that part too. So domain of g of j, and the square root issue, square root restriction, said that we cannot square root a negative. And if we can't square root a negative, then the inside had to be greater than or equal to 0. Which means if I solve it, I get x is greater than or equal to 5. So the domain would be bracket 5 to infinity. Now f of h would mean, let's get that function back so I can see what it is. F function starts it out, and I'm inputting h inside of it. H is 1 over, whoops, we don't need that yet. H is 1 over x minus 2. So that's going inside of f. So if I start with f, I have 4x minus 2. Now that x is the input, which is now h of x, 1 over x minus 2. So we've at least got this part. Now I can distribute, but think about what you're distributing. This is 4 over 1. And so if I multiply, I'm really only multiplying fractions. This times this becomes 4 over 1 times that is just x minus 2, and then minus 2. And we can leave it like that. That works for this function. We do want to look at the domain restriction f of h has, because this has a restriction of a fraction. So it has a rational function in it. And anytime you had a rational function, you wanted to ask yourself, I can't divide by 0. So when is this denominator going to be 0? So denominator cannot equal 0. So x minus 2 cannot equal 0. And then we solve it out. So x cannot be positive 2. If we looked at that on a number line, we'd see every value shaded in except for positive 2. So we go from negative infinity up to 2, union 2 to infinity. And so those 2's are both going to get parentheses because they're excluded. It cannot equal 2. The last one here, E, says h of g. So h of g means that I'm going to start with h and input the g function. H is 1 over x minus 2, so 1 over x minus 2. And now let's input g. G is 3 minus 2x squared, so 3 minus 2x squared. Now we can see if we can try to simplify that, but the only thing we're going to be able to do is just combine some like terms in the bottom. So I'd have a negative 2x squared, and then 3 minus 2 is just 1, so plus 1. And that's all that you can do with this function. And that's fine. It doesn't have to simplify any further, but the domain for this, domain of h of g, has the same restriction of where the denominator cannot be 0. So our denominator is negative 2x squared plus 1. And it's a quadratic. So the ways that we tried to solve a quadratic were by factoring, or if there was only one x value, we can just solve it like normal. So I could subtract 1 and then divide by negative 2. When I divide by negative 2, I get a positive 1/2. And to undo our x squared, we square root both sides. So when we create the square root, we are doing the operation of square rooting both sides. We have to do plus or minus square root of 1/2. And those are our two excluded values. X cannot equal positive square root of 1/2 and negative square root of 1/2. And so if you looked on a number line, you'd find out where is that negative square root 1/2. It'd have an open circle. Positive square root 1/2, open circle. But everything else is okay. So let's write that in interval notation. We'd have negative infinity up to negative square root 1/2, union negative square root 1/2 to positive square root 1/2, union positive square root 1/2 to infinity. Now in the next video, we'll look at this graphically.